able to see the presentation. So we have seen the limitations of thermodynamics, and we have seen very important terms which are very often used in thermodynamics. Say, for example, system. System is any specified portion of a matter under study which is separated from the rest of the universe with a bounding surface. Surrounding is the rest of the universe in a position to exchange energy and matter with the system. Now we have seen what are all isolated system, closed system, and open system, and we have also seen the macroscopic properties, that is the properties of the macroscopic system, or the molecules of very big assemblages. Say, for example, pressure, volume, temperature, composition, density, viscosity, surface tension, refractive index, color. So they are all macroscopic properties, and these properties can be divided into intensive properties and extensive properties. Intensive properties means they are independent of the amount of the substance. Whatever may be the amount of the substance, these properties will not change. Extensive properties means they depend upon the amount of the substance, the mass, volume, energy, they are all depending upon the amount of the substance. Suppose if you take a small quantity of the substance, the mass will be less. If you take a very big quantity of the substance, the mass will be more. So the mass depends upon the quantity taken. But the density is the mass of the substance of a unit volume. So we are dividing the mass by unit volume, means whatever may be the quantity of the substance taken, the density is not going to change. Similarly, viscosity is not going to change according to the quantity taken. Similarly, specific heat capacity will not change. Refractive index will not change. Surface tension will not change. So these are all the properties which are independent of the quantity of the substance. And also we have seen the different types of systems, homogeneous systems, which is uniform throughout, or the system which contains only one phase. And a heterogeneous system, it is not uniform, or it is a combination of two or more phases. And in each phase it is homogeneous, but as a whole, the phases are immiscible. And we have also seen what is the state of a system. When all the macroscopic properties are found with a definitive value, then the system is said to be in a state. When one or more macroscopic properties change their values, now what happens? This change results in the state changes. So the state variables, we have seen what is a state variable. When a system moves from an initial state to final state, there will be certainly a change in one or more state variables, like a pressure, temperature, volume, mass, composition. And we have also seen what are all the dependent state variables and independent state variables. Suppose if a single gas is present, then the composition of the gas need not be discussed, because the composition is always 100%. So the composition becomes a non-variant. If it is a closed container, then there is no chance for addition or deletion of the substance from the system. Therefore, no point in discussing the quantity, that is the mass. So mass is not a variable here. So similarly, we have seen what is thermodynamic equilibrium. So when the macroscopic properties of a system do not change with the time, then the system is said to be in an equilibrium. In each phase, the macroscopic properties remain the same. Say, for example, thermal equilibrium, which means that there is no flow of heat from one part of the system to another. Therefore, the temperature remains the same in all parts. Mechanical equilibrium means no mechanical work is done by one part of the system on another part, where the pressure remains the same throughout. Chemical equilibrium means the composition of the various phases remain unaltered with the time. Say, for example, you are taking nitrogen gas, hydrogen gas, and they are reacting, and ammonia is formed. Now, this system is said to be in a chemical equilibrium, which means that the reaction is continuously going on. Nitrogen is combining with hydrogen, forming ammonia, and simultaneously, ammonia gets decomposed to give nitrogen and hydrogen. But if you look into the system, both the reactions are continuously going on. But if you keep the container as such for several years, and if you come back and see, even then the reactions will be going on. But the composition, that is the quantity, that is the equilibrium quantity of nitrogen, the equilibrium quantity of hydrogen, and the equilibrium quantity of ammonia will remain the same, whatever may be the time duration after which you watch the system. So the composition remains the same. It remains unaltered with the time. So that is chemical equilibrium. That is why the chemical equilibrium is given a very beautiful definition. It is the apparent state of rest. It appears to be at rest. It is an apparent state of rest of two chemical reactions proceeding in opposite directions with more or less the same speed. So that is the composition remains the same all the time. Then the system is said to be in a chemical equilibrium. Now look here, if a single substance is taken, then the properties will be an extensive property. So the single substance property depends upon pressure, volume, temperature, and the number of moles remains a constant because it is a single substance. There is no addition or deletion. So the P, V, T are the three variables to be considered, and even among them, one of the three variables is interdependent. Therefore, it is sufficient to mention only two variables. Say pressure and temperature is sufficient. Intensive property, pressure, volume, temperature, any two of them have to be mentioned. If it is a mixture, then for extensive property, pressure, volume, temperature, any two of them, and then number of moles of A, number of moles of B to be mentioned. For an intensive property, any two of the pressure, volume, temperature, and then the concentration, because when the composition changes, the intensive property changes. Say, for example, I want to explain here. See, the extensive property is independent of the quantity. Now you are taking a mixture. So in the mixture, say I'm taking phenol and water mixture. 1 liter of phenol is mixed with 1 liter of water. Now, in order to note down the extensive property, certainly the mentioning of the 1 liter of phenol and 1 liter of water is very much essential, because when you change the quantity small, even a small quantity, the total quantity changes, total the parameter changes. But when you speak of the intensive property, which is independent of the quantity of the substance, you have to mention the concentration. When you change the concentration, density will change. See, density is independent of the quantity, but density will change when the concentration changes. Suppose I take 1 liter phenol, 1 liter water, now the density is something different, even though the total quantity is 2 liter. I am taking half a liter water and 1.5 liter phenol. Now the total quantity is 2, but the concentration changes. Therefore, the intensive property changes. So for a mixture, in order to consider the extensive property, you have to mention the number of moles of each component. But in the case of intensive properties, you have to mention the concentration of the system. Now, the another important concept, the operation by which a system changes from one state to another is called a process. Say, for example, I will be explaining the same concept with a diagram, then you will understand the operation by which a system changes from one state to another is called a process. Certainly, there will be change in energy, sometimes in matter also. If the process is taking place at constant temperature, there is no temperature change during the process, then the process is called isothermal process. For an isothermal process, there is no change in the temperature. For an adiabatic process, the heat supplied is zero. That is Q is equal to zero. If you are not able to understand anything now, don't worry. When you study further, you will understand what is this adiabatic. And another thing is isobaric, where there is no change in the pressure. Actually, delta means a change. Delta P means a change in pressure. So for an isobaric, the delta P is equal to zero. For isochoric, actually this isochoric is not written. It is isochoric, the volume is zero. That is the change in volume is zero. So these are all the four types of processes. And again, the process can be divided into two types based on the speed of the process. See, some processes are called reversible processes. Reversible process means any process which takes infinite number of steps and each step is infinitesimally slow. Suppose it is a very slow process. Actually, naturally speaking, we can say that there is no reversible process in nature. Suppose for understanding, I can tell you the blossoming of a flower. See, if you look at the bud, the petals are closed, and when time goes on, the petals are slowly stretching out and the flower comes. But the rate of stretching out of the petals is very slow, reversible, which takes infinite number of steps and each step is infinitesimally slow. Even the growing of our nail, see, every minute it is growing. But after a week, if you see, your nail might have become longer. But if you continue to look at your nail and wanted to note down that it is growing, it is not possible because it takes infinite number of steps and each step is infinitesimally slow. Our hair growing, even our own growth, the growing of a plant, these are all reversible processes, very slow processes. But the efficiency of the reversible process is very high. If an irreversible process is very fast, waterfalls, water falling down from a distance, explosion, a balloon exploding, any sudden process, a fast process is called irreversible process. So reversible process, the process which takes infinite number of steps and each step is infinitesimally slow. Irreversible process, anything which is very fast in rate. The fast processes are irreversible process. Thermodynamically speaking, the efficiency of an irreversible process is almost zero. So the efficiency becomes very high only when the restoring force also becomes very high. Now you look at this diagram, now you can understand. So I have taken three cylindrical pistons which are frictionless, three frictionless cylindrical pistons which are confined with a gas. Let me say it is an ideal gas. So inside the piston, the gas is found. You know, any gas has a particular pressure. So actually this pressure is the manifestation of the collision of gaseous molecules on the walls of the container. That is what is actually happening. Suppose if this cylinder is filled with a gas, the gas molecules are not stationary according to the kinetic theory of gases, and the gas molecules are experiencing constant collision. and there is no energy loss during the collision, and the gas molecules are not colliding with each other. They are not only colliding with each other, they collide on the walls of the container also. So when they are colliding on the walls of the container, they are exerting a pressure on the wall that is in all directions. Therefore, as the piston is made of some rigid cylinder, you need not consider the pressure on the other walls. You can consider only the pressure that is acting on the piston to make it move up. So the pressure of the gas which is inside this container is pushing the piston up. At the same time, the atmospheric air has a pressure which pushes the piston down. Now, if the pressure that is external and the pressure that is internal, if these two pressures are equal, what happens? There is no mechanical work done by the system with the time, because there is no pressure difference. As there is no pressure difference, there is no mechanical work done by the system. So the system is said to be in a mechanical equilibrium. So I have already told you, for a thermal equilibrium, the temperature must be uniform throughout. Therefore, there is no heat flow from one part of the body to the other part of the body, because all the parts of the body are at the same temperature. Similarly, for a mechanical equilibrium, there is no work done by one part of the system on the another because of the uniformity in the pressure. So here, the pressure of the gas inside the piston and the pressure of the gas outside the piston, if they are equal, there is no flow of matter. So there is no mechanical work done. So the pressures remain constant with the time. So it is in a mechanical equilibrium. Suppose I am reducing the external pressure by a small quantity dP. So dP is infinitesimally small quantity. What is infinitesimally small quantity? Suppose, let me take the internal pressure P to be 1 atmosphere. That is, the pressure inside the cylinder is 1 atmosphere, and the pressure outside the cylinder, let it be 0.99999 atmosphere. So what is the difference between the internal pressure and the external pressure? 0.00001 atmosphere. So what happens? The external pressure is different from the internal pressure by a very small quantity, which is called the infinitesimally small quantity. So when the pressure difference is very small, even negligible, what will happen? The piston will start moving up, because the external pressure is infinitesimally smaller than the internal pressure. So now the piston goes up. This is called the expansion of the gas. So the gas expands infinitesimally slowly. There is a very slow expansion, very slow. So this slow process is called a reversible process. Suppose if the pressure of the gas which is inside the container is P, and the external pressure is almost zero, let me say almost zero, there is no restoring force at all, there is no the external force acting on the piston at all. If it is so, what will happen? The piston will go up at a faster rate. It will be even like an explosion reaction. So in that condition, the fast movement of the piston in the upward direction is called irreversible expansion, a sudden expansion. But the work done in this irreversible expansion is zero. But the work done in the reversible expansion is maximum. So the work done depends upon the strength of the external pressure. The external pressure should be low to make the system expand, but at the same time, the difference between the internal pressure and the external pressure should be infinitesimally low. So the very small difference that is between the internal pressure and the external pressure is making the piston move in an infinitesimally slow rate. There is a very small expansion. That small expansion is called the reversible expansion. So there is a state change. So when the change in state is observed, there is a change in energy also. This change in energy is appearing in the form of heat, work, and light, and etc. And that will manifest in any form of energy. So, heat is a form of energy, work is a form of energy, light is a form of energy, sound is a form of energy, even material deformation is also a form of energy. Suppose a balloon is breaking down with a pump sound, the sound is a form of energy. Even the breaking down of the plastic material, the balloon material is also a form of energy. So energy can come out in the form of mechanical work, in the form of heat, in the form of light. But these are all taking place just because of the change in the state of the system, whether it is a chemical state or physical state. There should be a state change to produce change in energy to make some work done. So this energy is expressed in CGS system in terms of erg. What is one erg? A resistance of one dyne, if it is moved to a distance of 1 centimeter, then the energy used or the work done is one erg. Suppose you are taking a resistance of one dyne. That one dyne resistance is moved to a distance of 1 centimeter. What is the energy spent or what is the work done? It is one erg. So 10 power 7 erg is 1 joule. So normally we calculate energy in terms of joule in SI unit. Sometimes the energy is expressed in calorie also. Suppose if you are eating idli or sambar or vadai or any other food material, it is calculated in terms of a calorie. What is the calorie? What is the number of calorie you have eaten? Suppose if you are having a treadmill, when you are running the treadmill for so much time, you can see the monitor displaying the quantity of the calorie burnt. What is the calorie burnt? So you are eating calorie and you are spending calorie. So there are some people who eat more calories and spend less calorie. What will happen? The excess calorie will get stored up in your body in the form of fat. That is why people are becoming bulkier and bulkier. So what is the calorie that is consumed should be used up. Even medically we are speaking, the energy required for basal metabolism. Even if you are not doing any work, some amount of a calorie to be supplied to our body to maintain the body. That is a basal metabolism. Your heart is functioning, lungs is functioning, kidney is functioning. All the parts of the body are working continuously in order to meet out the energy requirement of the continuous functioning of basal metabolism. You have to provide some amount of energy and you have to eat a little more for your own activities. You are cycling and you are walking and you are working, you are studying, you are listening, you are teaching, and all these things are energy consumptions. So in order to meet out the basal metabolism and also the external work done, you have to take totally so much calorie of the food. But one thing is, whatever calorie that is consumed should be burnt off. If it is not burnt off, then the excess calorie will get deposited, and that deposition will lead to so many complications. So the joule, you should always understand the relation between the joule and the calorie. One calorie is a 4.184 joule. So joule is a 4.184 into 10 power 7 erg. 10.7 erg. Suppose if you are not able to remember this relation, you see 8.314 joule is equal to 1.987 calorie. So both are the gas constants. You know one thing, the gas constant, universal gas constant R can be given various units. In SI unit, it is 8.314 joule per mole per Kelvin. It is 1.987 calorie per mole per Kelvin. 0.082 liter atmosphere per mole per Kelvin. So these units are equal, means then very easily you can calculate the relation between joule and calorie. So the joule is a 4.184 into 10 power 7 erg, 4.184 joule, which is equal to 1 calorie, which is equal to 1 calorie. Now listen, my dear students. Now listen. So this is the energy. So this particular point you have to understand very well. Normally energy, it contains two factors, namely intensity factor and the capacity factor. So look here, I am having a cup of tea and I say the tea contains energy of 20 calorie. Let me say it contains energy of 20 calorie. But if you measure the temperature, it is say some 60 or 70 degrees centigrade. At the same time, you are taking an ice cream, which contains 50 calorie. But the temperature, if you measure, it is 0 degrees centigrade. So the temperature which is measured using the thermometer is not actual heat content of the body, it is the temperature of the body. So there is so much difference between the heat content and the temperature. You cannot measure the heat content using a thermometer. Suppose you have some 1 ml of petrol. If you measure the temperature, it will be 20 or 25 degrees centigrade. But if you burn the petrol, it liberates a heat energy which is measured in terms of joule or calorie. So any energy is discussed in two different factors, namely intensity factor and the capacity factor. Wait for some time. See, suppose heat energy, intensity factor is a temperature, capacity factor is a heat capacity. See, when you multiply this intensity factor and heat capacity, you are getting the total heat energy. See, temperature is a T, mass, specific heat capacity is heat energy. Mass, specific heat capacity, and change in temperature, it is expressed in kilojoule. Suppose electrical energy, number 5. So electrical energy, voltage is the intensity factor. Quantity of the electricity is the capacity factor. What is the quantity? Quantity is a current into time. What is the current? That is, current is expressed in ampere. Voltage is the potential difference. Ampere into time. Suppose 1 ampere current is passed for 1 minute. So 1 ampere into 60 seconds. This is the quantity of the electricity in coulomb into voltage will give you the electrical energy. Potential energy is mass, which is the intensity factor. Capacity factor is mass into gravity into H, where H is the capacity factor. So energy, intensity factor, and the capacity factor. When you multiply these two, you are getting the total energy. So this is about the energy. I think now